I'm Kiera. I'm one of the co-authors of this paper alongside my colleagues from the University of Birmingham. And I'll be revisiting assumptions on membership inference attacks for summary statistics. Health-related studies use summary statistics, such as averages and standard deviations, in their publications. Using aggregate data prevents revealing actual patient information. For example, samples are taken from N people. They get gathered into a distribution that conveys meaningful information without exposing any individual. The often private nature of an individual's data attracts the attention of those who wish to exploit sensitive published statistics, especially if inaccessible sensitive information is revealed elsewhere in the journal. Prior work examines whether an adversary with an exact copy of someone's data can infer whether they can contribute their information to a particular public study. However, possessing exact data from the time of the study is infeasible. Plus, information may change or have gaps and discrepancies. So let's consider our adversary only gains access to something less precise and more realistic, such as data collected at a different time. We can model this as the original sample plus some noise. This change could be significant to the attack for time-sensitive data, such as microRNA expressions, and is something to investigate. MicroRNAs are small, non-coding RNA molecules that regulate gene expression by binding to messenger RNA and inhibiting protein translation. They are actively focused on in medical publications to identify the impact many diseases have on gene expression. Unusual microRNA levels often indicate presence of illnesses. However, expression levels fluctuate over time due to everyday behaviors like diet. We use these two current state-of-the-art tests for membership inference in summary statistics. They are used for a hypothesis test to decide whether the target's data aligns better with the study or the general population. Here is how they're defined mathematically. Note that the L1 distances test only uses averages, while the LLR test considers the standard deviation also. Other tests using same published quantities will face similar complications against what we are stress testing. We consider the cases where an adversary wishes to infer membership, but only manages to collect noisy or incomplete data. Their access to population-wide summary statistics is assumed, as it is simple to gather. First, we examine the performance under synthetically generated noise, such as Gaussian noise. Then we extend this to the real-world noisy scenario, where data values have drifted from the time of the study. Secondly, we check inference where several of an individual's dataset features are unknown. Our experiments are performed on 3 datasets. 2 contain microRNA expressions from diseased individuals, and the third extends our results outside of genomic data. 2 of these datasets contain real longitudinal results. After pre-processing, we divide individuals from these datasets into a simulated study cohort called the pool, leaving those remaining to form the population that simulates the general public. Averages and standard deviations are taken feature-wise for all groups. For our cross-sectional dataset, we evaluate 2 types of pools, one using individuals sharing a disease trait, and the other by sampling uniformly at the same size. In comparison, the longitudinal datasets only contain participants who share the same disease or have no identifying unique traits, allowing us to test the attack performance against a population of similar yet non-participating individuals. When we cluster individuals with the same disease into pools, we see that both statistical tests perform quite well. The inferences continue to succeed despite increasing levels of Gaussian noise and large portions of microRNA information missing, with AUC dropping by only 5% from 466 microRNAs down to 100 microRNAs. When these 2 noisy features are combined, we see subadditive results. We found that smaller size pools are more resistant to noise due to the amplified individual contributions to the statistics. Further, higher feature dimensionality extends noise tolerance. Here are the same tests performed with random pool samples. Interestingly, while performance remains good, the AUC drops by around 10%, and the TPR and 1% FPR more than halves compared to inferences only using diseased individuals. This highlights that something disease-related inflates the more realistic inference performance we see here that wasn't previously considered. With further examples, it is obvious that the disease case study pools consistently outperforms randomly sampled ones, regardless of the pool size. In our paper, we bounded from below the minimum error of any membership inference test on summary statistics and quantified a signal term that contributes to this performance error. The signal term is made up of a small subset of features with condition-related shifts. What we are seeing in these experiments is the impact of disease signals misclassifying non-participating individuals as accurate attacks. We repeated the experiments on several same-size stratified data samples, and the same pattern always emerges, validating our theoretical result. Next, we replicated the tests using realistically noisy longitudinal datasets. Notably, performance drops to near random guessing whenever we use data taken from an alternate time. We show with the dotted lines the expected performance on the microRNA dataset when using synthetic Gaussian noise with independent features, highlighting how much synthetic noise underestimates real drift. To identify the cause of the degradation, we test whether the noise can be replicated on group level, as the synthetic Gaussian noise applies variance per feature. Marginal feature level variance alone cannot be the explanation. We transplanted the drift vector from the nearest neighbour, which is determined through Euclidean cosine and correlation distances. However, this also broke the structure degrading the attack. This shows that the degradation is related to each person's own temporal drift. No other individual's drift, similar or not, can reproduce this. We also tested whether the population structure is responsible for the collapse via a leave one out conditional mean test. We approximate an individual's drift from baseline with linear regression from the remaining population. However, this attack performed similarly well. When collecting all results together, we can see that only each person's own temporal evolution can decrease the attack to near random levels. The asymmetry between the nearest neighbour and real drift implies that the cause of this is not merely random variance. Hence, the reason behind the performance gap is specific to each individual. It remains to be seen whether a stronger attacker can exploit this structure or if temporal drift is a basis for defense. In conclusion, the L1 distances test scores remained higher for longer under synthetic noise. This is due to the test only considering averages, and Gaussian noise having a zero mean that averages out over many features. Meanwhile, LLR complements the L1 distances weakness by using the additional information from standard deviations to withstand higher levels of missing data. Should an adversary estimate their own noise level, they can select the superior test. Both tests conflate disease signals with correct inference, as shown when testing randomly sampled pools and as predicted by our theoretical result on minimum error. Finally, real temporal drift cannot yet be reproduced synthetically. While this may be good news from a defense perspective, exploring the reason behind the performance collapse from individual temporal drift, as well as confirming our findings over other data sets and domains, are avenues for future work. Thank you all for listening.